Let's take a look at section 2.8, Meeting Expectations, on page 257. This section covers expected value and weighted grades. If you turn to page 258, I've actually already gone through and done the rolling of the die, so you don't have to sit and watch me do that or listen to me do that. You could try it on your own. It's kind of interesting. It's interesting to see how it works. Basically, we're rolling a die and we're recording the number that showed up each time we rolled it for 100 rolls. Then they ask me to do several things. In question number 1, they ask me to add up each row, and then they ask me to add up all the numbers. Basically, I want to know what total I won. So my answer to question number 1 would be that I actually won $379 in this game that I'm playing. Number 2 asks me, on average, how much should I win per roll? Well, I take the 379 divided by the number of rolls I had. How many rolls did we have? We had 100. So on average, I won about $3.79 per roll. If we had more of these, we would do question 3. We don't have any more, so we won't do it. And what we have basically found in questions 2, and if we could have done question 3, is we found the expected value of this game. It's the average amount we expect to win. So we would expect to win $3.79 on any given roll. The question it asks here, though, is it possible to win this amount on any one roll? Can I win exactly $3.79 on any roll? No. Why not? Because my only possibilities are either $3 or $4 on any given roll. I can't win 3.79 on one roll. Question 5 asks me, what is the probability of getting a 1 when rolling one die? How many 1s are there when you look at a die? There should be just one. How many total sides are there? 6. So the probability of getting a 1 is 1 over 6. Turn to page 259 and we'll continue with this idea. What is the probability of getting any individual number from 1 to 6 when rolling the die? Well, each number only shows up one time and there are 6 sides. So the probability for any given number is 1 out of 6, or 1/6. They ask us to use this information to complete this table. The probability of winning $1 is 1/6, because that's the probability of rolling a 1. The probability of rolling a 2 is 1/6. A 3 is 1/6. These don't change unless we have some sort of weird weighted die. All of my probabilities will be 1/6. As for the amount we win, we are going to multiply. I like how this describes this. We multiply the previous two columns. I take 1 times 1/6 and I get 1/6. 2 times 1/6 is 2 over 6. It goes against everything we've ever learned, but let's keep it in unsimplified form. What would 3 times 1/6 be? 3 over 6. So we're multiplying the first column by the second column. 4 times 1/6 is 4 over 6. 5 times 1/6 is 5 over 6. 6 times 1/6 is 6 over 6. Let's see what else they ask us then to do with these numbers. Number 8 says to find the sum of the values in the third column. So we're going to add up all these numbers. I know that it's going to be something over 6. Let's add 1 plus 2 plus 3 plus 4 plus 5 plus 6, which should be 21. Let's go ahead and convert that to decimal. It should be 3.50. So we expect to win $3.50 per roll. How does it compare to the expected value we found? We found $3.79, so we were actually pretty close. The more numbers, if we could have done 1,000 rolls, we would have been even closer. The more rolls you get, the closer you are to that expected value. Number 9 says, obviously playing this game for free would rock, because I'd be just winning free money. You'd always win something for nothing. How likely is it that to happen in real life? Probably not very likely that they're going to let me play for free. Instead, you'd typically pay to play. What do you think would be a fair price to charge to play this game? Well, if my expected value is $3.50, if I charged $2 to play the game, I would lose money. If I charged $3 to play the game, I would make money. And I just said that wrong? Not $3 because it's $3.50 is my expected value. If I charged $4 to play the game, I would make money. So charging $1 or $2 or $3, I would actually lose some money. If I charged $4 or $5 or anything more than that, I would actually make some money. Turn to page 260. Oh no, we have one more question here. Question number 10 on this page says, let's say you were setting up this game somewhere on your campus. Would you expect to make money if you're charging students $2 to play? No, I'm going to lose money because I expect them to win $3.50. How about if I charge $5? Yes, because I only expect them to win $3.50 with any given roll. Now we can turn to page 260. They go through the steps on how to find an expected value. You list out all the possible numeric outcomes. You write the probability of each outcome. You multiply each numeric outcome by its probability and then add the results. That sum is your expected value. So they have set up a chart for us here. If I am charging $2 to play, it's going to change the expected outcome, expected winnings for the person playing. So if I roll a 1 but I paid $2, I'm actually losing $1. If I rolled a 2 but I paid $2 to play, I break even. If I rolled a 3 but I paid $2 to play, I'm earning 3 minus 2 or $1. So what I'm doing for each of these is subtracting how much I had to pay to play. My mouth is not working well today. The probabilities are exactly like they were before. 1, 6, nothing changes about that unless we get some funny die. And then the very last column is found by multiplying the quantity or the amount of value, the amount we're going to win, times the probability. Now they ask me to go up and add these again. This is towards the bottom of this chart. It says, let's go ahead and add the values. So it's going to be something over 6 again. -1 plus 0 plus 1 plus 2 plus 3 plus 4 ends up being 9 over 6, or $1.50. I would expect that if I was paying $1.50 to play this game, if I was paying $2 to play this game, my expected winning now goes from $3.50 to $1.50 per roll. I would expect that I would win $1.50 for any given roll. At this point, you should be ready to do your group work, which starts on page 261 and goes through page 264.